starting of the deep learning part. Okay, so many of you might have already had more or less acquaintance with artificial neural networks, but I'll stick to basics. Uh, there might be many participants who have not been, they know the name, but everyone knows the name, but let's see what goes inside artificial neural networks. We'll do some hand calculations, we'll do some simulation, and we'll see what are the nuances involved with artificial neural networks. So, see, first we try to understand where this term is coming from. So, artificial neural network, they provide the sort of exciting alternative method for solving variety of problems, starting from regression to classification. It is multi-dexterous. So the applications are unlimited, and right now also you might see an application of artificial neural network around you, maybe your phone or your uh, personal assistant or whatever it may be. So there's no point in talking about machine learning unless you know artificial neural networks. Basically, the goal of ANN is to make intelligent machines. Machines basically where an input goes and there is a processing and there's an output. That's why we saying it as a machine. They're generally significantly used in solving complex problems. So some applications of ANN before we go ahead so that it may look interesting to you. And we have seen all these things like speech recognition. We all use personal assistants on mobile phones. So that falls in gamut of pattern classification, handwrite, handwriting, processing, hand gestures, waveforms. So we see in healthcare it is applicable. It's applicable in signal processing. Clustering part also can be done with neural networks. So data mining, data compression, and the other aspects of exploratory data analysis, they are all possible through neural networks. Then function approximation, uh, sort of regression, you can say, and even combinatorial optimization, it has been used. So it's an NP hard problem, combinatorial optimization, and still a technique like neural network, if it's applicable, it gives a tough competition to other ways of solving the thing. Then let's see pictorially. If you look at these pictures, you might see here that it's indicating overfit. It's a sort of curve fitting what's going on. Its prediction is going on, and then image classification is going on. Image processing. You see optimization is there, and then the predictive aspects of predictive maintenance are indicated over here. Blood cell classification at the top, and you see clustering over here and the pattern classification. So many different problems could be addressed by neural networks. So that's why it is so important to understand the working of it. Although when it gets complex, the working really can't be, you can't really point out the reason why it's happening. At times it is also called as black box approach. We will see that why it is also called as black box approach at times. So the genesis of neural network lies in the neuron. So this is a biological neuron which you see over here, which is uh, we are made up of billions of biological neurons are there in our body. Although it was discovered in 1906, but by 1960s it became prevalent in mathematics. So you see here, a biological neuron has a nucleus, it has cell body, it has synapse, it has dendrites and axon. So the biological neurons are connected with each other through dendrites, and the signal, or you can say the electrical signal, which goes across our body, passes through these dendrites, and a sort of electrochemical reaction takes place at synapse, where the conversion of the electrical signal takes place. Okay, so this is a small intro to biological neuron. So since there are multiple in nature, they are woven across human body. Uh, are unlike our normal neuron, uh, unlike our non-human computer or the computer that we are using right now, the architecture of that is sequential. While the neurons, they are designed. The neural network is designed for massively parallel distributed processors. So if each neuron is a processor, then they are parallelly distributed. That means, uh, let's say you are looking at a tree, and your perception is that the tree is about to die. It's a frozen. It's sort of old tree. So this signal is not perceived by only single neuron, but millions of neurons are going to perceive this tree, and a conclusion will come to your mind that, okay, this tree has lost all its leaves in a green season, so probably it has completed its life. So that's why we say it's massive parallel distributed processors, because not one processor is working, but millions of processors are working together to conclude that statement about the tree. So it has the capability of storing experimental information, knowledge, and use it for future. Why do we say it's experimental? Because if you see the learning of human beings, we do experiment and then we learn. That's why we say, no, practice makes the man perfect. That simply means that you have to generate a lot of experimental data, so that eventually you will know what is the right way of doing it. So that's why it is saying that it has the capability of storing experimental information. So our learning, the human learning, is absolutely dependent on the neurons which are there. So and slash knowledge is given because the data is processed and then it is stored in inference. So we will see that it is configured for a particular applications. So what it simply means that the neurons are not generic. For different activities, there are different set of neurons. That's why some people are good at playing, and some people are good at music, and some people are good at literary writing. For the simple reason that the neurons are rich in that particular domain in a given person. And that's how the heredity also goes across the family, where you would find a particular talent uh, prevailing across the generations. Although it's not generalizable statement, but then that's why you see that's happening, because the neurons are biological and they carry information across the generations, and that's why Everyone can't be good at everything, but everyone is good at something. So there you see the particular application of um, configuration, specific configuration of the neurons. So they are not generic in nature. So a small recap of that, how the construction of the neuron is goes. So nucleus contains information on hereditary traits. So the nucleus which is there in the middle of the neuron, in the center of the neuron, the hereditary traits are there in that, and the plasma containing the molecular equipment for production of material needed by neuron. So plasma is important from
हेलो
that aspect.
हाँ 800 अच्छा अच्छा
And then neuron receives signals from other neurons through dendrites. This I had already told, and transmit signals along an axon, and then eventually branches into strands and substrands. So the information goes through these as impulses, and at the terminals of the strands are the synapses, where the two neurons are contacting each other. Now you can see that how fast the electrical signal passes across. When you see a object coming towards you, you take an evasive action, and you see that the information which has been um transmitted through your eyes across the neurons, and it reaches to the hands as an evasive action. So how fast is that? So the reaction time of a human being tells that how fast the neurons, how rich the neurons are. Generally, in old age, that reaction would be slow, but in when you are young, that reaction would be higher. That's why the sports person has life limited to 35, 40 years. After that, the neurons don't regenerate that fast. So then the impulse reaches the synapse terminal to release neurotransmitters. These neurotransmitters diffuse across the synaptic gap, and at the synaptic gap, the presynaptic electrical signals get converted into chemical signal, and then back to postsynaptic electrical. So electrical signal to chemical, and then back to electrical. That's what happens at the synaptic gap. So the effectiveness of synapse can be adjusted by signals passing through it. Now that's the whole idea, that this adjustment of the signals uh, indicates learning. So once these signals are well attuned to an activity, you would say that you attained perfection in doing activity, or you attained a good level of professionalism in doing that activity. So this effectiveness of synapse, so this adjustment, this particular word adjustment is the core of artificial neural network. So that's what happens. We try to adjust the weights which are given to these various synapses, the neurotransmitters which are there at the synapse, that what kind of signal which is coming as a perception should be given, how much weightage, so that your neural network can give you the desired output. So that's the whole thing. So what scientists have done is they have tried to mathematically model this process, and uh, there we have the artificial neural network. So some of the stuff which is there in the slide, I will try to uh, go across it because we have limited time. So much of the numerical part I'm taking. So this is for your future learning. Where you can share the slides. You can see that how the neurons are different than the non-human computer that we use. You can see it later. So we can go ahead and see that it's McLelow's-Pitts model, where you see a generic representation of a neuron, where the multiple inputs are coming in terms of x1 to xn, and the weights are there, where individual how much weightage has to be given to what input is given as w1 to wm, and they are going as an input to a neuron where the uh, processing will take place. The processing can be done with activation function. So various functions are represented over here as activation functions, like threshold function, a linear function, then Gaussian and sigmoid function. These functions are some sort of they represent the natural processes which may be happening, and the conversion of the signal takes place through these functions, and then you get the output. So let's see. So if you have two inputs and one output, we call it as a perceptron. That's the simplest form of neuron, you can say, is the perceptron. Uh, just to see, how many of you are carrying paper and pen? Because it will be nice if you can work it out, if you have to really understand it. So we're taking a very small example here. You can raise hand, or in the chat box you can say that whether you're having pen and paper or not. I'm just checking in chat. So one person has said that he's having, yes, yes. Okay, few people have. Okay, good. So I think we can do that now. So let's take down this thing. Let's try to understand what is this weights about. So what I've talked about earlier is that the weights are given to the inputs, and what we do is input is as you give the input, the processing of the input will take place through an activation function, and the output will come. And here we are talking about supervised learning. That means I know what output I want. So I can get the error. So inputs are there and some random value of the weights initially we will give. And then you're going to get an output. And that output, if it's matching the desired output, then you say your neural network is well trained. If it's not matching, then we need to update the weights. How do we update the weights? Is this way, where W new is representing the updated weight. W old is the old weight which was already there, with the use of which we have calculated the output. And delta W is the change in the weight. And how do we calculate delta W is eta target minus output and xi. So xi is the input vector, uh, and then t is the target output, and o is the actual output where the activation function was applied, and eta is the learning rate. So learning rate, for now, you can take an analogy of whether you're doing, whether you're reading a book too fast or too slow. If you read a book too slow, then it might take time, but your understanding will be much better. If you read too fast, then you complete the job, but your understanding may be not that great. But if it's too easy book, then you can probably understand it faster, and learning rate could be higher in this case. But if the book is too complex, it has to be read slowly. If you then only your objective will be met. So you can imagine it sort of like a simple novel, a cliched simple novel. You can just go through the pages fastly, and still you would understand the story. But if it's sort of a investigative novel or a detective sort of a novel where a lot of ups and downs are there, then you might actually miss some good information, and then in that case, your learning rate should have been slow. So that way you can understand it. So let's say we take a small example of a perceptron where two inputs are there, and so this is the AND gate. Let's try to understand what is the use of gate over here first. So when the
Excuse me, sir. Can you explain what is the meaning of weight here?
wait. So
Yeah.
weight basically means that if you go back, I did talk about effectiveness of synapse can be adjusted by signals passing through it. So signals passing through it basically means that how much weight is, so larger signals are passing, that means higher weight. If lesser signals are to be passed, then the smaller weight. Similarly here, or you can say when you're trying to learn us how to ride a cycle, there are several inputs when you're trying to ride a cycle. Could be uh, center of gravity, it could be the speed, it could be the tire pressure. Many things are there as an input. So uh, given a basic understanding, I believe that in order to balance a cycle, the center of gravity has to be given, the location of the center of gravity has to be given the highest priority, you can say, or more weightage. So with multiple inputs, what value should that input be, so that you are able to balance the cycle. So although you do this or do all this involuntarily, uh, your body would do that, adjusting the weights and what be the numeric value of that. That is all happening naturally. But if you have to do it artificially, then these values are to be adjusted. You have to give a way of adjusting these values. You have to tell the algorithm how to adjust these values. So these are the weights. Am I clear over here?
Yeah, okay, sir. Thank you.
So here you would see that this is an AND gate, and uh, here target values are given as it should be there in AND gate, like 0 if the input is 0 and both the inputs are 0. The target value which should be is 0. Similarly, it's for all the 4 rows. And we are representing target value 0 by -1 and target value 1 with +1. So that is our representation. For mathematical tractability, we are doing that. You can represent it any way you want, but this is more applicable in that sense. Then you have the we take a learning rate of 0.4. Now it can be taken randomly, or uh, how do you take it? Because consider you're doing any new thing first time in life. So where do you start? You just start by experimentation, right? You take any value in that sense. So the learning rate is taken as 0.4. The input nodes values are given as 1 and 2. And the two input nodes and one output node, that basically indicates it's perceptron only. And the initial weights are given as 0.6 and minus 0.2. They can be randomly taken. The learning rate can't be greater than 1. And that's how it has been defined. Although you can do mapping of it and do whatever you want later, but then the standard way of doing is that the learning rate should be between 0 and 1. That's how the mathematical expressions have been devised. The scaling can be done anyway. So initial weights and then the activation function has been chosen as a step function because it's easy to uh, explain also. And the activation threshold is 1.5. That means if your net input crosses 1.5, then your output is -1, else 1, right? So what do we do here is, let me see, I'll try to use pen also on the screen to work it out. So what we are doing is here, what we are trying to do is, we are trying to calculate the updated. So our objective is to calculate W new. Take a different color. So let's see for the first one where the input values are 0, 0. So how do I calculate the net input? Net input is weight multiplied with the value. So net input would be, so the, I think, have you taken down those values? I think you can take down the value. I'll just take you back. You can take down this, you take a screenshot of it or do whatever you want that way. So can I go ahead? Okay. So net input like 0 multiplied with the weight, which was 0.6 plus 0 multiplied with minus 0.2. So hence you get net input as 0 over here. Now, when the net input is 0, as per the threshold function, if net input is lesser than 1.5, the output has to be -1. This is the output, we get it as -1. So now we are in a position to calculate uh, the updated weight. So W new. So in order to calculate W new, I need to calculate adjusted weight. Okay, so delta W1, how do I calculate delta W1 is, uh, it's given as a learning rate as 0.4. So 0.4 multiplied with uh, target minus out, right? So target for when it is 0, 0, you can look at that. When the x1 and x2 values are 0 and 0, the target is -1. And minus, and the output is again -1. So -1, that makes it 0, right? Multiplied with the initial, this particular value of vector. So this 0, and hence you get it as 0 over here. So weight new or weight dash, you can say, would be uh, old weight. Old weight was 0.6 plus updated weight is 0. So hence it stays as 0.6. So there you see is the updated weight. Similarly, we do it for the second one as well, where the updated weight again remains the same as -0.2. So hence we are able to get these values. Similarly, can you try to do it for the second one as well? Try to work it out. Although it's not changing, but try to do it for the second one and the third one and the fourth one. I will do it for the fourth one. Meanwhile, you can try. I'll give you 2-3 minutes to try. Calculate the updated weights. You can see because of zeros and the cancelling out, the weights are not getting updated in the first 3 steps, but in the fourth step, it gets updated. So, can you please mute participant Poonam? Can you please mute? Okay. So, if you want me to do this again, let me know, or I'll wait for your calculation. Okay, let me do one thing. I'll do the calculation for the fourth one as well. I'll do the calculation for the fourth one as well. So now the input values are 1 and 1. So net input would be 1 multiplied with 2 formulas. Neeti is asking 2 formulas are used. So basically, okay. So let me show you. You may take down these 2 formulas are there. This is as simple as it gets. So 1 multiplied with 0.6 plus 1 multiplied with minus 0.2. So hence the net input here is 0.4. You can see this value 0.4. Net output now it is 0.4 and it is lesser than 1.5. So hence the output is -1. While looking at the AND gate, this should have been 1. This value output should have been 1 ideally. So we can see the difference over here. Now we can calculate the delta W1. So delta W1 is old weight. So it is the learning rate multiplied with target minus output. So here the target was 1, while the output is coming out as -1. Okay, and multiplied with the the vector. So we get this value as 0.8. Similarly, W2, delta W2 is also coming out as 0.8. And then we update it. So 0.8 plus 0.6 becomes 1.4. Hence, you get these values as the updated weights. Now you see the neural network has updated the weights. The objective of the neural network is to get the target value and the output value as close as possible to each other. So right now they are not satisfying. So now can you work out fifth, sixth, seventh, and eighth step? I mean, with the updated weights, you do it for the whole neural network again. So can you quickly do that? I'll give you 5 minutes. Let's say 9:50. So let's see if you can work it out. The solution I'll give you the next slide. If you have any doubts, do let me know. Okay, so any doubts? Can we go ahead? Anyone who's found out? Okay, tell me for 1 comma 1. Okay, Santlal. Very good. So 2.2 and 1.4 are the updated weights. Let's see whether he's right or not. So it turns out that the weights actually didn't change for 1.1, 1 comma 1 now. The net input is 2. That means this greater than 1.5. That means it becomes 1 now. Here you see with the updated weights 1.4 and 0.6. And the net output is coming out as 1. So you see here with the updated weights, all the outputs are attuned. That's how it should be. And we are getting net error as 0 across the network. So hence the final updated, and you would say here the neural network is trained because whatever is the desired output, it is giving the desired output. So this is about the perceptron. Now, some other aspects of neural network. I'll take you to a website where TensorFlow Playground. I'll share the link in that. Just give me. I'm sending one link. Open that link. I would suggest use a laptop. In mobile, probably you won't be able to. You can try that, but it will not be that useful. TensorFlow Playground. I'm sending the link in the chat. Rather, I'll send it in the WhatsApp group. Just open this link. This is a simulation of neural network, which will help you in understanding. So now let's see. All of us are here, and let's try to understand what is this TensorFlow Playground. So I'm having few slides about TensorFlow Playground. I'll share those slides first. Let's try to understand what this is, and then we will do some tweaks here and there. So this TensorFlow Playground, if you see, is a tool for applying the for applying neural network. So it is a way to visualize machine ML training that's happening in the with the help of neural network. It allows changing different components like training data, model loss function, parameter, other of the optimization algorithm which are there. Here the evaluation protocol is fixed because this is just for evaluation purpose. So it is mainly meant for experimenting with the neural networks, but we can repurpose it for understanding various different components of ML also. So it'll not nothing will happen. I mean, you can do as much experimentation as you want. Here, no initial data. You don't have to give any data. The data is pre-fed into this. Here the data is represented into two classes, that is a positive class and a negative class. There is the two different colors. So the positive class is represented with a blue color, and then you will see when it's there, and the negative class with the orange color. So these are some aspects you see that the optimization procedure is given over here. Optimization of the uh, neural network, and then the activation function part is over here. The model is built in this area, and this is the loss function. Loss function basically represents that error which you are having, and this is the evaluation part where you would see how your training and testing part is happening. So uh, I think you might, this is the fourth day, so some idea you might already be having about training and testing. If there's any doubt, let me know, or I'll assume that you know that already. And here the training data is there, so you can actually do some changes like batch size, ratio of training to test data you can change. And this is the visualization part where you take an inference that this is the best. Here you see the test loss is 0, the training loss is also 0. And the boundary over here is representing the segregation of the positive into the positive area and negative into the negative area. Okay, so there are some aspects which are covered here in this. That is the epoch. So epoch is basically number of samples processed before the model is updated, and epoch basically is that like we've calculated uh, weights and then we updated the weights. So from calculation of the weights to updating the weights, it's one epoch. Okay. And then the batch size is the number of samples which are processed before the model is updated. So right now, only one sample was, when we applied it on perceptron, only one sample, that is the input was 0, comma 0, that is 0, comma 0. But then you can feed input the vector also, complete vector as one input. So that complete one vector would can have multiple samples. So the number of samples processed before the model is updated, like together how many samples you are feeding in it to make it work faster. If you do one data point at a time, it will take a lot of time. So generally vectors are fed in batches of in batch with certain batch size, just like it happens in the manufacturing. The size of batch must be more than equal to 1 and less than or equal to the number of samples in the training data set. Of course, if there you got 100 samples in the training data set, and if you maximum that you can feed at a time is 100 only. So that's what it said. But then the keeping the batch size too large is also not advised, because uh, there is a possibility that your model may get confused with too much variation coming in. The larger the sample, the more variation it is carrying with itself. So that's why you have to adjust that also. And the optimization part, what is happening is the regularization is basically for I'll tell you subsequently. So here you can see that self learning rate, set learning rate, we can set it over here. Number of training iterations we can set over here. When we will play with it, then you will also understand what is the use of all this. And then here the weights can be adjusted. So I mean weights which are going in. When the neural network starts getting trained, you will get to know that which variable is given more weight and which variable is given lesser weight as compared to the others. The thicker the line which is connecting then the more weight it has. Loss function can't be explicitly stated. I mean, this simulation tool does not tell you the value of the loss function. It is changing with the type of the problem that we are taking. That is the error, of course, will change with the type of. So for in this particular case, a binary cross entropy function has been used. That's just for the information, not that it's got any relevance with we doing it right now. So regularization we will see at the end. So now we can play with that TensorFlow playground. So let's say we reset it and we remove the number of hidden layers. Nothing is there. Well, the term hidden layer, I would have taken one more. I think if I can take one problem, let me diverge from here, because the term hidden layer you might not able to understand it immediately. For that, I have to take a complex problem. Let's see, for half an hour we'll work on a complex problem by hand, and then we the remaining half an hour we'll do this TensorFlow playground. That you will get to know more easily than in that case. So I'm switching to a whiteboard where I'm working on a problem. Generally, this takes a lot of time. I've spent 3-4 lectures are going into the neural network. I have to condense that into 2 hours. So let's see if we can manage that. Just a second. So we take a new one. Now let's say we have got right now till now we have taken a simpler network, but let's see how a bit complex one works. So let's say we have a little bit of a complex network like this. Now we have a complex network. Earlier there were only 2 inputs. Here also 2 inputs are there, but 2 outputs are there. We got 2 outputs here. But how do we, so net input, how do we calculate the net input? We can calculate the net input to A. We can calculate the net input to alpha, beta also. Like this is called the hidden layer. and we may know the target value here, target alpha, target beta, we can say. Maybe we know these values, but how do we um, calculate the error which is there? Because uh, we can calculate the error till here and update the weights for these layers. But then how do we update the weight of A, B, and C? Because we don't know the target for A, B, and C because it's a hidden layer. And why hidden layer is there? Uh, as the network complexity grows, even if you look at the body, our human body, there may be one neuron which is taking the input. There may be one neuron giving the output. But in between that, billions of neurons are there which are interwoven with each other. And this signal, input signal, passes through all this. So practically, that's how it is. You can't just have one input and one output, and in between one process. You have multiple layers, and that's how the complex problems also work. So how do we get this weight? Let's say, so we take a snapshot of this situation and we try to calculate we try to develop an expression for calculating the intermediate layer weight. So let's say, so I'll just shift it slightly, come back to that. So let's say we have A as an intermediate layer. This is your output, B and C. This is WAB, we can say, and this is WAC. So this is hidden layer neuron. And these are the output neurons, output layer. These are the outputs. Now, so error at B, how do I calculate error at B? Error at B is output of B 1 minus output of B. Now, from where am I getting this? This is because, let's say, we are taking sigmoid function for reference as an activation function. This is the most prevalent one, sigmoid function. And for hidden layers, this activation function is more preferred. So not the hidden layer, but the output layer sigmoid function is preferred. So, and then you have target value minus output B. Okay, so this is the error, and why we are taking sigmoid is for demonstration. You could have taken any other function also, but that's generally acceptable. And with this, we update WAB plus. We can update the weight WAB plus. That's the updated weight. WAB old weight plus error B multiplied with output of A. Okay, so that's how we update the weight. So for outer output layer, this is how we can do. But for input layer, for A, how do we calculate the error? So let's say now we calculate, this is the similar way we can calculate WAC as well. So we calculate similarly WAC plus will be WAC plus error C multiplied with output of A. Okay, so we calculated WAB plus and WAC plus this way. Now error at A, how do we calculate error at A? So we can say error at A will be equal to, again, the sigmoid function, output of A 1 minus output of A multiplied with the error of B multiplied with the WAB That is the updated weight now. Sorry. Plus error of C multiplied with WAC. Okay, so that's how we do. Now, what we have done is we have went backwards. So that's why it is called back propagation. So what you do is first you calculate the net input. While doing that, so if you look at it, we went backwards. We actually went first. We calculated error. That means we went forward. Then after calculating the error at the output layer, we propagated that error backwards. So that's why it's called back propagation algorithm. So we can say this is back propagation algorithm. So that's what we do with the complex network also. Now we go here and we try to develop expression for this network. So let's say what do we do first is calculate errors of output neurons. I'm writing error as delta of output layer. Yeah, you're propagating the error backwards. So that's why it is called back propagation algorithm. So we are calculating error. So let's say alpha, delta alpha, that is delta alpha would be given by output of alpha 1 minus output of alpha. This is your sigmoid function. Target alpha minus output alpha. Similarly, delta beta would be output beta 1 minus output beta, target beta. Okay, so this is simple expression. After this, second is we update the weights. So we update the weights, that is, we can write it also over here. A alpha. So just larger. I'll write the errors, then make it small. You also do this. Otherwise, it will become cluttered if you don't follow it. No? Okay. Okay. So change output layer weights. We change the output layer weights, which will be WA alpha plus WA beta plus, so this will be WA alpha plus Here, while I was deriving that, I didn't use, I took learning rate as 1 while I was doing it for the back propagation, writing for the back propagation. Delta alpha output. So delta alpha basically is target minus output. So we have to multiply it with the learning rate as well. Sorry, A beta. So we do it, I'm writing it for the remaining one. I think you should also do it by hand. So for all the three, we are writing these weights. WC alpha plus beta delta alpha output C WC beta WC beta plus beta delta beta output C. Now we've changed the output layer weights. Now next what we do is after changing the output layer weights, we have to back propagate these errors and update the hidden layer weights. So for that, we have to calculate the error which is there at the intermediate layer or the hidden layer. So let's calculate the error at the hidden layer. This is step number 3, you can say. Step 3 is uh, calculate hidden layer errors. So delta A, delta B, and delta C, just the way we had written the formula earlier. So this will be output A, 1 minus output A multiplied with delta alpha, that is the error which is there at the output layer, WA alpha. Now here WA alpha is the updated weight, W delta beta and WA beta. That's how the error is propagating backwards. Similarly for the third one. So we calculate the hidden layers, layer weights like this. After calculating the hidden layer weights, we have to change the hidden layer weights. So this is the step number 4. So W lambda, if that is the updated weight between the input layer and the hidden layer. So here we updated the hidden layer weights also. Now, similarly, you can do it for omega 1 also. This is for lambda. So you can do it for shift 2. Now here we see that we have updated all these weights. Now let's see the bigger picture. So as we see over here, we had a dense network, then a perceptron. Omega and lambda were the input nodes, and alpha and beta were the output nodes of the output layer, and ABC was the hidden layer. Okay, and I needed to update. I used the backpropagation algorithm to update the weights of the hidden layer and subsequent layers. Any doubts in this first? So here what we did was we started from the last layer. We first updated the output layer weights. After updating the output layer weights, we changed the output layer weights. Then after changing the output layer weights, we calculate the hidden layer error. After calculating hidden layer error, we updated the weights of the input layer. That's how we did that. And this process keeps on going till the error is reduced to your liking, the liking of the user. For a complex problem, it's just not possible for it to be zero, the error. Just like human learning is not perfect, there's always a possibility of error. Same thing goes with the neural network also. There's always a possibility of error. Now we go to the TensorFlow playground. Any doubts in this? Generally, I would do a numerical problem also with all this formulation, but we do not have that much time where we can do a numerical. So we can go to the TensorFlow playground. Let me give you a 3 minute break just to digest it, and then we'll resume in 2-3 minutes. Okay, let's resume to TensorFlow Playground. Now, when we look at it, there are no hidden layers. There are two inputs, so it's acting like a perceptron only. Okay, and ratio of training to test data generally taken as 80%. This out of 100, 80 points will be taken for training of the algorithm and 20 points will be taken for testing of the algorithm. And let's assume there is no noise. And batch size, we can take it as 10. This is a standard. So 10 samples will go in at a time. And epoch, this learning rate, we can take it. Let's start with a small learning rate, then we can increase. Activation 10, activation function, we can take it as sigmoid. And regularization, basically what happens is regularization indicates it's a technique to reduce the overfitting. Overfitting means you're learning a problem. It's like two questions. It's like it used to, if you remember, it used to happen in history and social sciences or any other subject where uh, questions were given at the back of the book and you would just learn those answers of those questions by heart, and same questions were going to come in exam and you are going to reproduce those answers as it is, and you're going to score very good marks and get labeled as a very good student. But if the questions from the back of the chapter of a textbook does not come in exam, some twisted questions come, you are not able to answer that. So then in that case, you were actually, there was no learning in that case, only rote learning, you can say, or rote memorizing was there in that. So that memorization, at times what happens is these algorithms, no, they have a tendency to uh, memorize or memorize those data points and give output as desired, which is not good. So that's called overfitting. So in order to overcome that problem, this regularization is done. And L1 and L2 are regularization techniques. They prevent the overfitting. They use loss functions to discourage heavy weights being given to a particular variable. Uh, so L1 and L2 you can see here. So these are sort of L1 and L2 are regularization algorithms. One is a lasso algorithm and another one is a ridge algorithm. So someone had asked me earlier what is L1 and L2. So if you want to read about them in detail, you can do that. Basically, that happens after you've run the algorithm, you check for overfitting. Okay, right now, let's say that only happens if we are getting very high accuracy, uh, which is unlikely for a human learning. So let's see this. Now, what we do is we run it. We are taking a classification problem only, we are running it. So we run it and you see this, keep an eye on this part over here where you see test loss is 0.5 and training loss is 0.5. So this is very bad and the loss is very high in this case. This is what our desired output is. This is the desired output where the orange part should be there in the orange region and the blue part should be there in the blue region, but that's not happening. So, and your epochs have increased, nothing is happening. Now, if we, let's say, restarted and we increase the learning rate, the learning rate was very slow. Now you would see that you won't get great results, but you'll get it faster. That loss you are able to recover in very early stages only. So we redo that, and now we again increase it to 0.3. So we increase it to 0.3, and training and test loss has actually increased a lot. So if we take it beyond highest, so the testing and training loss is very, very high. And you see the orange color, so much of orange color is there in the blue one. So this is it. This is now what can we do to improve this? So let's say we again go to lower learning rate, let's say 0.003, and we add one hidden layer. We add one hidden layer and we start with one neuron. So you would see that what is the effect of adding a hidden layer. You can assume that a very, very non-complex organism, amoeba, might be having one perceptron. So it can't do much, it has no intelligence or very less intelligence. Or an ant, which may be having even lesser number of neurons and a less complex neural network. So hence less intelligent. So if we have to make it more intelligent, we have to add one hidden layer with one neuron, let's say. So let's see if we can reach somewhere. Although the testing and training loss has not improved by much, we can try to increase the learning rate. But increasing the learning rate will only get you so far. Fastly converging to the same solution. It's not happening. Still, this is not enough for this kind of data. So we may have to increase one neuron in the hidden layer. Let's see what happens if we make it more dense. If we make it more dense, we can see over here that probably we might get. So see the training and testing loss is reduced by good amount over here, and we are able to get somewhere. Although it is not happening. Now, can we increase the hidden layer? Can we increase the learning rate? If we increase the learning rate by much, the training and testing loss is slightly increased. Right. Now we try to improve more by adding one more neuron. We keep learning rate slow and again do that. Now you see that training and testing loss is again higher. Can adding more neurons improve the problem? Let's see that. So let's see one more neuron to the hidden layer. Does it increase? Does it reduce the test loss? No, it is not. So that means we need to add one more. Let's say we try to add one more hidden layer. We try to add one more hidden layer and increase one neuron at a time. So let's see if this increase makes it better. Testing loss is still high. So we add one more neuron here and again run it. Training and testing losses high. And learning rate we increase. So now it is reducing. We made it faster. So you see that testing and training losses become very, very less now. And it is almost 001. So you almost achieved it. It is almost zero. Testing loss is zero and training loss is also zero. So you see here, this is the neural network that you have been able to make, which is perfectly classifying the positive and the negatives. So that's what's happening is the learning over here is that there is no perfect way of doing there is no perfect way of approaching a neural net training a neural network. The user has to know the data. I should have awareness about the data. I should have awareness about various mechanisms with which we can improve the accuracy, or with which we can reduce the. So now you can, let's say if we increase the noise, what happens? If we increase the noise, let's say by 10 units, that is, noise basically means that your data is having some points which are mixing something in the signal is not coming perfect. For example, you are playing songs and you're recording a music for a song, and at the backside there is a constant hammering of some construction work going on. So that actually goes in the recording. Now, if you have to have the perfect music, you will have to remove that sound from the recording. So this recording is sort of a sample, and noise is that kind of uh, disturbances which are there in your recording of the samples. Getting it? So this is that part of the noise. So what is the effect of noise on your network? So let's see that noise. Your training and testing loss earlier was 0, while it is not reaching 0 now. This is the effect of the noise. And you would see over here that few points over here, these orange points, they are sort of misclassified points. What if I want to deal with the noise? Should I increase the batch size? Can I increase the batch size and try to overcome the noise? So let's say I increase the batch size from 10 to 16. So does it have any effect on the noise? So let's see. Yes, it has. It has reduced the noise. The test loss and training loss has reduced by increasing the batch size, because it is now catering to a larger variation. If I increase it more, can I get 0? So let's see we do that. If I still increase the batch size, I have been able to I have been able to reduce the test loss and the training loss by even more amount. And if the ratio of the training to test data uh, I increase to 90%, because noise is there, so more variation. So let's say if I increase to 90%, I'm able to reduce the training and test loss. So is it advisable to have 90% training to test data? Not always. For the simple reason that you should have ample training and test data. If you have less, if you have only 100 points and 90 points you are throwing in the test, in the training set, testing is very less then. So in this case, the probably number of points are larger. So we are getting good results. Now let's go back to the slides. Any doubts here you would like me to talk about? Now this is the premise of the deep learning. Now see here.
Sir, excuse me. Here, sir, classification is classless.
Sorry, I didn't get your question.
You have not selected any classification.
No,
If
it is
the classification regression, then what it could be? You have not
selected classification. Huh?
Regression
Okay.
rate also inflated, sir. So on that we should see.
So actually, we have to see whether there is an overfitting or not. So if you look at this testing, no, it is perfectly classified. I didn't see any overfitting. But if you let's increase the regularization rate, let's see what's the effect of that on this. It wouldn't change much with all this. Is the similar output we are getting even if we increase more regularization? Let's take it to 0.3. Does it give me 0? It still does not give me 0 with a very high regularization. Okay, so I mean that's what I was trying to talk that. So you can play with this tool and get more hands on the working of the neural networks. You have different data sets over here, like x1, x2. If you can increase the number of inputs, make it more complex, the learning would change and make it more dense with the number of neurons and the layers. Then you can see the show the test. This is the testing data. So you can tinker more with it, spend some time and get more hold of it. So that's what happens in the deep learning. You increase the number of the density of the neural network. So the denser the neural network, more complex problems it can handle. That's the idea behind it.
So here
You
batch
would-
size
Yeah,
20, can please re-explain it.
yeah. Batch size 20 basically means that whenever just a second. So whenever I'm inputting, inputs are going in, like when we did perceptron training, one input in a time 0 0, then 0 1. What if all these points together go in processing at a time? So if all these points go processing at a time, then let's say 20 points are going together at a time. So that's the batch size. Okay, I'll talk further. Few other nuances of neural network. Shall I stop sharing this TensorFlow playground now? Just stop it over here, and then I'm sharing this slide. Training and testing data. Is there a validation data set? See, validation data set in this particular TensorFlow, it's not there. But if you have ample, generally validation is done when you have ample data set to break it into 3 parts. If you have ample data set, then you can go for validation also. But generally, training and testing is what generally people limit themselves with. I'm just returning to the neural network slides. Not this one. This TensorFlow we have done. There are a few things that we observed that what are the parameters for ANN. So parameters are these, we call these parameters are the variables that the model learns from the training data. That is the weights. And biases, I didn't talk about the bias because we are talking about the elementary part. So one expression of bias is also included while we are updating the weights. It's when we are going ahead. So bias basically is that over a period of time, your, let's say, model is constantly making some error uh, because of the bias. So there you get a chance to update the bias and reset the neural network to get it to, it's sort of a zero error. Okay, so if I have to avoid the zero error, I can use bias. So these are the constants added to weighted sum of inputs at each neuron. Hyperparameters. So all those changes and hit and trials which we're doing with the samples, with the batch size, with the noise. Noise is actually not a hyperparameter. Noise is something which is observed, but then that was induced to show the effect of the noise. So the number of layers, number of neurons in each layer, these are all hyperparameters, activation functions. Hyperparameters, why they are hyperparameters? Because they are not the output of your algorithm. They are going as, these parameters act as tuning parameters with which you tune your algorithm by, these are sort of hit and trial, you can say. How do you get to know about these hyperparameters? With the experience. First time a person is handling a particular type of data, and the first timer who's making that neural network will have to do a lot of work in tuning the hyperparameters. Once it is tuned, then or you already understand the data, then tuning these hyperparameters is much easier. Slides are not coming. I'll share it again. And then learning rate, all these are your hyperparameters. Although here optimizer we did not choose, but optimizer is also there where it helps in optimizing the, just a second. So all these things are there, like loss function, and then the Adam optimizer is a common optimizer used to update the weights of the network while in the training. There's another term called bias variance trade-off. I'll share this in the slides so you can go through that. It's again sort of it's the inability of machine learning method to capture the true relationship between variables, and is called bias. That is, uh, if you see, if you are trying to fit a linear line through points versus a curve through the points, so there is a high possibility of the squiggly line to pass through all these points than a simple line. So there is a bias in fitting a simpler curve, where linear regression may exhibit higher bias but show relatively lesser variance on testing data. Now, this is initially when you are fitting a line, the bias will be high for the linear regression as compared to the non-linear. But when you are going to do it on testing data, at that point of time, you are it was doing very good the curve was doing very good with the testing data, but when you are going to give a new data, that is the training data, there is a possibility of higher variance in that. But for a linear regression, it may be lesser. So that's the bias variance trade-off. That is the complex. If you take a complex curve, there is a possibility it may be showing more variance in the testing data. So, and this is an example of overfitting where uh, blue dots are for training and green for testing. So, uh, when you are training it, it will learn all these points, and when you fit a give new points, then it may start giving the worse results. So that's again overfitting. And then we use regularization to reduce the overfitting. I think we had a lot of content for today. So I think I'll stop over here. If you have any doubts, you may ask. So what we talked about today about neural networks, and then subsequently how neural networks go into the deep learning part, where and neural networks are basically replication or your neural network of human being is translated to a mathematical model. Although the workings are pretty simple of a neural network, but it can handle very complex problems. The basic premise of neural network was that we update the weights, and that's all what we have seen happening across. So, any doubts? Anything you'd like to discuss? You may write in the chat box or. Okay, Amar was asking why output, why we used output A 1 minus output A. Basically, why we did that was it was a sigmoid function. So the processing has to be done. No, how the input get processed into output is through that activation function. So we chose that activation function as the sigmoid function. Yes, anyone else? Shinu, you're there?
Yes, sir.
So if there are no questions, we may conclude.
Yes, sir.
Okay. I'm on mute for a few seconds, few minutes, 1 or 2 minutes. Then we'll conclude.